Now, it's over budget and took much longer than planned. It will also only run 6 days a week.
Back in May, the long-awaited and over-budget Elizabeth line opened.
That's terrible. Yeah, it's going to disrupt most of our commuting to and from London.
The Elizabeth line was constructed using different advanced engineering techniques, including TBM, SEL, and segmented lighting systems. Now, a vital part of London's transport network, the Elizabeth line did not come into being without challenges. What began as an ambitious project to improve mobility for Londoners soon faced the harsh realities of buildings through a city shaped by centuries of growth. Adding a new railway beneath one of the world's most congested underground and surface environments presented a host of complex obstacles. Today, we delve into the remarkable story behind its construction, uncovering the trials, breakthroughs, and critical moments that brought the Elizabeth line to life. A staggering 4-year delay. What exactly went wrong? The reasons are many, ranging from financial complications tied to contracts and executive salaries to unexpected incidents that arose during construction. First, the challenges of building in a dense urban environment. Construction took place during the 2010s, a period when London had already reached a state of near saturation. Centuries of development had created a maze of infrastructure, existing underground lines, skyscrapers, sewage systems, all layered across both surface and subsurface. Navigating around these to safely carve out a new route proved to be a formidable task. TBM might seem like just a tool for digging, but in reality, it requires an incredibly precise path to be set. For instance, when digging near Tottenham Court Road Station, the TBM had to pass through a space just 35 cm away from the escalator's structural base. Additionally, it had to navigate only 85 cm away from an active tube line. In other words, the precision required was so high that it was as if the machine had to clear a path with the smallest of margins.
Structure.
This is our TBM.
Yep.
This is the pile bottom.
Wow,
And that's what we got in between.
It's unbelievable.
That's how good we are.
Almost like threading a needle. In such tight spaces, the precise navigation of the TBM was made possible by Tunis navigation system from VMT. Tunis is a highly accurate system capable of millimeter-level precision, continuously tracking the TBM's real-time position and correcting any deviations. Here is how it works. A laser transmitter is set up near the tunnel's starting point. This transmitter sends a laser beam along a pre-designed reference line, guiding the TBM along its intended path. Inside the TBM, a target unit is installed to detect the laser beam emitted by the transmitter. This information is then continuously tracked by a total station, a precise measurement device which calculates the TBM's current position and direction. In curved sections, relying solely on the laser transmitter becomes challenging for maintaining accuracy. To compensate, additional devices like reflectors and gyro sensors are used to correct the path. All of these processes are integrated into the Tunis software, enabling the TBM operator to make real-time adjustments to the machine's direction. As a result, thanks to the Tunis system, the TBM was able to safely complete its journey along the predetermined path, even through the complex and sensitive underground spaces of the city, without any collisions. This ensured that there were no incidents such as debris pouring out from beneath the TBM, which could have caused panic among passengers. Secondly, the ground subsidence problem occurred during the tunnel excavation process, which affected the stability of the surrounding buildings. Around 21 kilometers of underground tunnels were constructed for the Elizabeth line, cutting through the heart of central London. Given the dense concentration of buildings above ground, managing the risk of ground subsidence became a critical concern. When tunneling takes place, the surrounding ground loses its equilibrium, leading to the ground deformation. In the case of TBM, the pressure at the tunnel face and the tunnel lining help support the ground, somewhat mitigating this deformation. However, in soft ground like London clay, it is impossible to avoid ground movement entirely, unlike in rock formations. This occurs because the removal of underground soil or rock causes the surrounding to lose its previous support, leading to the deformation ahead of excavation phase. Additionally, there is always a time gap between excavation and lining installation, during which further ground movement can take place. When subsidence occurs, there is a risk of damage to the buildings above. To mitigate this risk, extensive building damage assessments and monitoring were carried out. Overall, the tunnel sections experienced minimal ground movement and the impact on buildings was negligible. This was consistent with the actual recorded results during construction. Especially in the western section between Paddington and Farringdon, which passes through the London clay, the volume loss was less than 0.5%, below the conservative damage threshold of 1%. However, there were some exceptional cases. Areas around stations in particular required deeper excavations, and horizontal deformation was more significant. Tottenham Court Road, for example, had many existing underground structures such as the London Underground lines, sewage systems, and communication cables. With the high density of buildings above ground, the tunnel had to navigate carefully around these structures, leading to a winding path for the crossrail tunnel. As a result, the SCL method, which is more suited to curved sections, had to be used. This method involves spraying shotcrete as the space is excavated, but it results in relatively larger ground subsidence. In contrast, Canary Wharf offered more ample space and a simpler structure, making it suitable for the use of TBM. It works by excavating the ground at the front while simultaneously assembling concrete segments at the rear to form the wall lining. It even applies phase pressure at the excavation phase to prevent the ground from collapsing right from the moment of excavation. In other words, with a TBM, excavation, support, and wall lining happen almost simultaneously, leaving little room for the ground to loosen. In summary, the ground subsidence in the Tottenham Court Road area, where the SCL method was primarily used, was relatively significant. This was especially true around areas like Tottenham Court Road Station, where there is a high concentration of historically valuable buildings, making them a focus for meticulous monitoring. The Crossrail project implemented a 3-step building damage assessment to predict the risk of subsidence for each building and to develop measures for those buildings that were likely to be affected. The taken measures included compensation grouting, where TIM injection pipes were installed underground to inject grout at high pressure, encouraging ground uplift and compensating for subsidence. Additionally, reinforcement structures were installed and buildings with defects were pre-repaired. To monitor ground and building displacement, observation equipment with a traffic light system was set up, allowing for real-time risk management. Despite these measures, there were instances of cracking. In those cases, immediate action was taken through crack repairs and enhanced monitoring to track the condition and prevent further damage. An additional challenge was the issue of noise and vibration caused by the tunnel construction. During the construction of the Elizabeth line, numerous complaints arose from residential areas due to the noise and vibration, necessitating the implementation of measures to address these concerns. In fact, the Humber Street Tunnel was delayed due to noise and vibration problems, which eventually led to a permanent suspension of construction. Due to the installation of tunnel vents and emergency exits, the construction was halted and soundproof walls and noise-absorbing panels were installed because of residents' resistance from excavation noise as they collided with dense dwellings. Nevertheless, it was not completed in the end due to persistent resistance from residents, adding to problems in local commercial districts. As efforts were made to avoid clashes with existing underground lines, perform construction with a minimal space, and address noise and vibration issues, the project inevitably proceeded more slowly. This week, we cover the delays that occurred during the tunneling process. In addition to this, there were many other issues that arose during the construction phase. So, in the next week, we will explain the contract and signaling systems as well as the financial challenges and how they were resolved. In weeks 7 to 9, we will discuss the construction methods and structural systems used in building the Canary Wharf station, including its roof and garden. Finally, in weeks 10 and 11, we will wrap up the presentation series by sharing the overall story of the selected building.